guys been? It's been a long 2 weeks.
It's been there's been definitely quite a bit happening. The Amy one was last week, which was mostly fine, though I did misread one of the questions when I thought the radius of the circle around the triangle was the side length instead, and so that was not so
Bad.
great, but it happens.
Hmm.
Reading is
Reading is
non-trivial.
hard.
I
It's
guess for
okay.
me, like, well, college, second semester of college started at the beginning of this month. Well, technically January 31st, but yeah,
Same difference.
it's been fun. There's a new set of classes, obviously, and I'm taking elliptic curves this semester, which I'm very excited for.
Fancy.
Wow.
Yeah.
Fancy. Yeah, I don't know. This February has been like very eventful for some reason.
I guess, like, statistically speaking, February is, has the least events in it, but I
Wow.
think that's a
Wow.
bit besides the point. But one event I'm really looking forward to is Valentine's Day, because guess who I'm seeing for Valentine's Day?
Who are you seeing for
Ooh.
Valentine's Day?
Ooh.
Oh, I'm going to be seeing math for Valentine's Day.
Okay.
Wow.
I got excited for like no reason.
Yeah, I
Yeah,
mean,
but
what else were you expecting?
I don't know. That's something interesting. But I guess I guess when it's Holden, I don't know what would I expect.
Okay, I see how it is.
And so in this episode, we're going to be talking about like more math related stuff. And so since February is, besides the other things we said, also it's Black History Month. So we wanted to, get started by talking about, contributions of some noteworthy Black mathematicians.
Yeah, so let's get right into it. The first mathematician that we'll be talking about is Dr. Gladys West, whose main contributions was in the world of satellite geodesy.
Just wondering, Isabella, what is geodesy for those audience members who might be curious?
I think geodesy is like they study the measuring and like the measurement of the Earth. In particular, you care about its exact shape because it's not exactly a sphere.
Yeah, there's a lot of aspects of the Earth that make it kind of hard to uh, model precisely. There's lots of variations in elevation and the whole Earth and water stuff. There's lots of variations. So
Like being wider at the equator than at the
yeah.
poles.
Also,
Mhm.
rock density like
Mhm.
influences ocean
There are
water level.
just lots of like really tiny things. So the entire field of satellite geodesy is trying to model that in a way. Is trying to model the Earth in a way that would be, I guess, perceptible by satellites. So this was like several decades ago, and
How
Dr.
long ago
West
exactly?
this was back in the 1970s. So, Dr. West's contributions were programming the IBM 7030 stretch computer to account for every force that would lead to variation of the Earth. And keep in mind, this is on a computer that was the size of a fridge.
Wow.
Then, after that, she wrote a guide on how to further improve it, as she foresaw further um, things that could be added to make it go faster. And in addition, she single-handedly brought down the processing time of their algorithms. Like she cut it by half. And eventually her work became like hugely relevant for the world of GPS, which we still use today. So she was a pioneer, and she laid down the groundwork uh, for the GPS system that we know today.
Yeah, thanks for
Yep.
sharing, Isabella. And I
Yeah,
guess
I would hate to not have GPS.
Yeah. I use Google Maps like every day. I'd get so lost.
that is very true. Yeah, I guess the next mathematician we'll be talking about is Dr. John Urschel. And Dr. John Urschel, well, actually, something really cool about him is that he recently got his math PhD at MIT, which is where I'm at right now. But what he did was he focused on numerical linear algebra and did work in machine learning and spectral graph theory.
What is spectral graph theory?
Well, spectral graph theory, I think, well, let's take a look here. And here, I think first, in order to introduce spectral graph theory, what I should really do is introduce graph theory itself. So for those viewers who haven't heard of graph theory before, What a graph really is it's just a collection of lines and dots that like can represent certain things about our world. Do you guys have like good examples? Like one thing I can think of is like computer networks, right?
Or
I was thinking like cities and roads.
Yeah,
there's a
that's another good
classical and like one thing to note is like you don't really care about the positions of the dots. You don't really care if the lines you draw are straight. You just care about what's connected to what. Another classical example is like friendships between people, maybe like on a social network, like who's friends with whom on some social network or something.
Yeah, like I'm friends with Luke, but not with Holden.
Wow. Okay. Anyway, so I think like one thing that's important in spectral graph theory, well, since I introduced the notion of a graph here, one thing that's important in spectral graph theory is the notion of an adjacency matrix. And that might sound like a really scary word to you, but it's actually a pretty simple concept. So a matrix is just a collection of numbers. And the way we're going to construct an adjacency matrix from a graph is, well, first let's give all the dots names. I think these are more commonly referred to as vertices, right? Like this.
I think single letters would be names, but sure.
Well, mathematicians are very boring people, so.
True.
Yeah, you're right, H.
Okay, L. Anyway, so to construct the adjacency matrix of a graph, like what you can do is, well, some pairs of vertices like A and C have an edge connecting them, right? So in
In this case,
our,
an edge is just a line.
yeah,
I don't know if that's
sorry,
already been said.
I should define that. So an edge is just a line. And in our adjacency matrix, what I kind of want to do is everywhere there's an edge, I'm going to put a 1. So there's an edge between A and C. And similarly, I'm going to put in a 1 here because, if A is connected to C, then C is connected to A. Like that's kind of obvious. And you can do this for like all the other ones. A and B are connected, so we put 1s here. Do you guys see where else we should put 1s?
Between B and D?
Yeah, B and D.
B and E.
B and
D and E.
D and E. Did I do this correctly?
Looks good to
Oh,
me.
that's right. And you might be wondering, how about the pairs of vertices that like don't have edges in between them? So like, what do you do with A and E over here? Well, what you do is you put zeros. So let's put zeros here, right? In all the remaining places.
What about the diagonal?
Yeah, that's a very good question. So let's look at this entry here, which corresponds to like A connected with A. And you might ask yourself the question, is there an edge that connects A to A? And the answer is no, right? So we're going to fill in the diagonal with zeros as well. And what spectral graph theory is really all about is like looking at these kinds of matrices, and associated with these kinds of matrices are these special values called eigenvalues. And I'm not going to fully explain what they are, but they're kind of like roots of
like
some
basically, because the nice thing, like, Holden said that a matrix is an array of numbers, like Holden said, but like when you have a matrix, it's sort of, this is the thing in the field of math called linear algebra, where you can sort of like, you can look at a matrix as like doing some sort of linear map on some numbers where, you're like adding numbers somehow, and you like, it's a bit complicated to explain, but somehow like when you have a matrix, there's a lot you can do with it. And so
Yeah.
it's really nice to have a matrix. And
a nice way to think about it is a root to a polynomial is kind of like an eigenvalue to a matrix.
In fact, a matrix has there's a polynomial associated to a matrix called its characteristic polynomial, where in fact the roots of the characteristic polynomial are exactly the eigenvalues of the matrix.
Oh, that's really interesting.
Yeah, so all of this has like deep connections with algebra. And one question that I think is really important to ask whenever you're doing mathematics is, why is this useful, or why is it important? And I think one reason caring about the eigenvalues of a matrix is important is because the eigenvalues control a lot of important aspects about the graph that the adjacency matrix comes from. So for example, one property that you might care about is like the average degree, or like maybe I should explain what degree is, but like basically the average number of edges coming out of each point. So like that's an important quantity you might want to care about, because you might want to care about, on average, how many friends does a Facebook user have or other social network, right? And another thing you might care about is like whether or not a graph has a bottleneck, because, well,
What do you
graphs with
mean by a
bottleneck.
bottleneck?
Well, that's actually a very good question. So like a graph with a bottleneck, let's give an example of a graph with a bottleneck. So an example of a graph with a bottleneck might be the following graph, like this. And it's basically a graph where you can split it into two halves where, there's very few edges between each half. So eigenvalues are very important when studying properties of graphs like these. Well, before we get too ahead of ourselves, I think one really, really cool thing that I didn't yet mention about Dr. John Urschel is the fact that he was formerly in the NFL.
Whoa, really?
He
Wait,
played,
so oh yeah, what position did you play?
yeah, he played lineman for the Baltimore
Ah.
Ravens.
Oh, that's
And I
so
think that's really
cool.
cool. Yeah. And then he switched into math, got his PhD at MIT, and then, now he's at Princeton. I tried looking on his, math.mit.edu webpage and looked at like all the like dozens of papers he's published, and they're all like very scary, to say the least.
Oh. Why did you drop out of football? Dang.
I heard that they said that like part of the reason was because he was concerned about studies about NFL players like getting brain damage from playing football. So
Mm,
I
football's
think I get enough
dangerous.
brain damage from doing math all
yeah.
day.
He had enough of that kind of brain damage. Time to move to a different kind.
Yeah, we do not. We're just joking here, to be clear. I think you all should do math.
Yeah. And if you like football, you should do that too. But be careful.
Yeah.
Safety is important.
Math really is, a lot safer than football.
Mhm.
But, to each their own.
I did sprain my ankle at a math contest once. That's a long story.
Yeah, so what is the next topic we're going to be moving on to?
I mean, wait, there's to give people a little more to say about like spectral graph theory, there was actually a problem on the Harvard MIT math contest in 2019 that had something about, there was a graph and then it was something about like you want to put a number on each vertex and you want like the sum of the neighbors of a vertex to be some constant times that vertex's number. And so and then there are some conditions about whether some numbers being like not being zero or something. But like this is basically the condition for when the constant number, like the constant multiplier, this is basically the condition about, Holden, you're missing an age. Yeah. The condition about like when a number is an eigenvalue of a graph. This is basically the condition. And so this is sort of it's a neat case in like a relationship between this sort of seemingly very advanced field of math, spectral graph theory, and like a problem that showed up on an actual high school contest. So yeah, this is 2019 February HMMT algebra/number theory problem 9. If people are curious.
Wow, we get it. You memorized all
Wow.
the problem numbers of every single contest you've ever done.
Not quite.
There we go. All right. For those of you who are interested, you can check that out on the HMNT website.
But yeah. So yeah.
But yeah,
And
what is our next topic?
so yeah, now we want to, stay somewhat true to our Curious Cube roots by being sure, we answer questions from viewers. So we
Let's
had
get
a
into our first
question
one.
from viewers. Nicholas asked, "What is Zorn's lemma?" So yeah, okay. So Zorn's lemma. This is kind of, it's kind of a difficult topic because this gets into some, whenever you're talking about infinity, it's going to be a pretty difficult topic. But let's try to talk about it. So okay, basically.
Well, first, what area of math is Zorn's lemma dealing with?
Right.
First of all.
So this sort of relates to the very foundations of math. And so, when you're trying to like make the foundations of math from the basics, this has been done from sets. So in the area of set theory, So, and basically a set, you can think of a set as like a collection of some objects, and it doesn't have any repeated elements, and it's sort of like some elements are in the set and some are not. Now you have to be careful with sets, because if you allow just anything to be a set, then you can come up with some paradoxes. Like, oh, you take the set of all sets that don't contain themselves. Does this set contain itself? Like if you just are too loose about sets, you run into paradoxes.
This is
So you
known as
want
Russell's paradox, by the way, I think, if you guys
uh,
are curious.
so yeah, like you want to be very careful about having some firmer foundations for set theory than just do whatever you want and oops, we ran into a paradox and broke math. You don't want to break math. So you want some firmer foundations. And so there's a set of axioms for set theory. Um, and so, but one of the axioms is a bit strange. The standard set of axioms is called the Zermelo-Fraenkel axioms with choice. So what is choice? Because that's one of the axioms. And so and when I say axiom, it's like a foundational statement that we use as a foundation of other stuff, and it's sort of like a basic assumption that is like you build other stuff from it, but you don't
Can
prove
you
it
give an
yourself.
example of an axiom?
Well, like in set theory, some of the axioms are sort of not very controversial. Like, if you have, a set, you can take a new set containing all of its subsets. That's the axiom of power set, I think, is a thing.
I
Actually,
think there's even a more simple example, which is pairing. It says for any two sets or any two things to be colloquial, you can create a set that has those two things in it.
uh, yeah. And so like so some axioms are like very basic things, but then you have the axiom of choice, which is like it kind of gets weird because, why do you like basically you get some paradoxes, not exactly paradoxes, but like if you have finitely many sets and you want a non-empty sets, like each of the sets has at least one element in it, and you want to choose one element from each of the sets, then you just sort of basically you just do it one set at a time. If you have a finite set of sets and you want to choose one from each one. But if you have an infinite set of sets and you want to choose one element from each set, then like you don't like none of the other axioms could let you like I think it's like you can run into some issues with this if you don't have an axiom that lets you do it. And so you have the axiom of choice to let you do things like this, to sort of you can make infinitely many choices all at once. You're guaranteed that it's possible to do that.
It's like a failsafe.
Well, it's just like you need to be sure that you are allowed to do things. Like you need to like be sure that you're allowed to do things with infinity or something like that.
I think a
Like
good
Sure that you don't
intuitive
run into
example
any
is
out
like,
of bounds glitches.
yeah, I think a good intuitive example is like, suppose you have like an infinite number of drawers and like, the drawers you use to store your clothing, or sock drawers. Let's use sock drawers. And each drawer has some number of socks in it. What the axiom of choice allows you to do is select one sock from each drawer all at the same time.
Yeah, like if you have infinitely many, this is sort of a classical example. Someone said like if you have infinitely many pairs of socks, the axiom of choice will let you choose one sock from each pair. Now if you have, or I'll say, an infinite set of pairs of socks, there are some issues where there are things that are too big to be sets, but that's a topic for that is beyond the scope of this episode. Such an object would be called a proper class, which you can look up if you're very curious, but that's beyond the scope of this episode. But the point
That's too
is,
curious for the Curious Cube.
well, is anything really too curious for the Curious Cube? But it's a little bit too curious for this episode.
Yeah.
So, I mean, okay, maybe there are some things that are too curious, but maybe not that. But not for today. Anyway, but the point, like, you don't always need the axiom of choice to make infinitely many choices. Like, if you had, like, suppose instead of infinitely many pairs of socks, you had infinitely many pairs of shoes, then you don't need the axiom of choice to do that. You're just like, I will take the left shoe from each pair, and then you've made your choices without needing any sort of fancy axiom. But for socks, it's like, how do you know that any choice exists? You don't have a distinguished sock. Left and right socks are indistinguishable. So you need like, you can't make infinitely many choices at once. You don't have a distinguished sock, so you need something to let you do that. So that's, that's the axiom of choice. And now there are other things that are equivalent to the axiom of choice. Or
Well,
sort
we
of
were
like,
supposed to be talking about Zorn's lemma, right? So do you want to
right. So the
explain what the
Zorn's lemma is
connection
one of
is?
those things that's equivalent to the axiom of choice. And
And what does
I'll get to
equivalent mean?
like basically given the other axioms, they're sort of like you can prove each one from the other. And yet, like another example of something equivalent to the axiom of choice is there's the well ordering theorem, which tells you that like if you have a set, then you can make an ordering on its elements where you say like for every pair of elements, you say you have a way of saying which one is less than the other one, and it has to satisfy good conditions like if x is less than y and y is less than z, then x is less than z, and you can't have no element is less than itself, and
It also needs the
if
smallest element as well.
like if two elements, you can't have two elements each of which is less than the other. Like I guess that sort of follows from the other two, but yeah, like that's just any old ordering. But then a well ordering is like any subset has a smallest, any non-empty subset has a smallest element. So like if you have the positive integers under their usual ordering, it's well ordered. If you take like the set of prime numbers, its smallest element is 2. The set of Carmichael numbers, its smallest element is 561. Any non-empty set has a smallest element, whether it's finite or infinite, it has a smallest element. Whereas the real numbers under their standard ordering is not a well ordering. You can have 1, 1/2, 1/3, 1/4, 1/5, 1/6, and that doesn't have a smallest element. There's always something you can go to that's smaller and smaller.
Well, isn't the
In
well
that
ordering
set.
principle supposed to guarantee some sort of ordering on the real
Well,
numbers?
yes, but so in this case, the point is like you just have to find some other ordering where the notion of less than is not going to be the same as our usual notion of less than on the real numbers. So this is another one of those things that is like you get some very strange things with trying to do things with infinity, and this turns out to be equivalent to the axiom of choice. And
I think you
so
can see like a good connection or an intuitive connection between axiom of choice and the well ordering principle is that like if you're trying to select, one sock from like infinitely many drawers, what you can do is if we know the well ordering principle is true, you can just well order all the drawers and then pick the smallest sock in each drawer. But without the
you
well
could
ordering
like
principle, you
you
can't
could
do that.
well order the union of all the sets, like the set that has
Yes.
everything all in it together. You could well order that and then just take the smallest one. So yeah, that's sort of how you could see the well ordering principle implies the axiom of choice. The other implication is not so obvious, but is true, I think. But now, to get back to our topic, what is Zorn's lemma? And so when we say lemma, you might be thinking of a small rodent of the polar regions, but that's a lemming. It's not a lemma. So
Or you
we are
might be
not.
thinking of a small yellow citrus fruit. That's a lemon, not a lemma.
uh,
But for today's purposes, we are talking about Zorn's lemma. And so a lemma is like a that's Lemma, and that's like a math result that you use to prove other things. And so Zorn's lemma also tells you something about these partially ordered, about sets that have some sort of an ordering. But in Zorn's lemma's case, it's like it's not necessarily totally ordered. You can have just like saying when one thing is less than or equal to another, and they satisfy some axioms, but you can have two things that are not comparable, where like neither one is less than the other. It's just two different things where neither one is less than or equal to the other. They're just incomparable. And so this is a partially ordered set because the order does not need to be total. It can just be some things are ordered and some aren't. So it's just a
I think
partial
a good
order.
example of this is just like subsets of the integers ordered by the like inclusion relation, right?
Of like one set being a subset of another. So
Yeah.
like, the set 1, 2 is a subset of 1, 2, 3, 4, 5.
So in a
But
sense, you can say 1, 2 is like less than 1, 2, 3, 4, 5.
but the set 1, 2 and the set 1, 3, 4.
They're not comparable.
Yeah, you could take like 1, 2 and then 1, 3, 4, and it's like neither one is a subset of the other. They're just not comparable.
Yeah.
And so Zorn's lemma is a bit technical in that, like, sort of informally, it's like if you want to find it's almost like you're trying to find the top of a partially ordered set. And basically, like, I think it's like, if you have, because, okay, in a partially ordered set, a chain is a set of elements where every two of them are comparable. So Zorn's lemma says that if you have a partially ordered set where every chain has an upper bound, and this is like there's some element of the post set that has, that is greater than or equal to all the elements. So like if for any chain, there's some element that's even above it, then there's a maximal element, that there's an element of the post set that has nothing above it.
I guess an example of a chain using the same example would be the set like 1, and then the set 1, 2, and then the set 1, 2, 3, so forth
Because
and so
everything
on.
in that is comparable.
Yeah,
Yeah.
and an example of an upper bound would be the integers or the positive integers, the set of all positive integers.
Yeah. And so, like, if this is another one of those cases where infinity is sort of weird, because, like, if you have a finite chain, you just if you have a finite non-empty chain, you just take the top element in the chain. But if you have an infinite chain, it just sort of goes up. You don't know where it's going to stop, and maybe it never stops. And so with this, you sort of have some sense in which, like, if it never stopped, then somehow, like, the set would become too infinite, and it sort of would become one of those things that I mentioned earlier, a proper class. It would become too large to be a set at all. And so, this is sort of one of those weird things about infinity. And this apparently is also equivalent to the axiom of choice.
I think to finish up our discussion of Zorn's lemma, we might want to state like some kinds of things that could be proved using it or why it's important, right?
Yeah.
So an
I think
example of
every
Zorn's
vector space has a basis, like this statement here,
yeah,
But I don't want to introduce those terms, but if you know what they are, you
Ah.
can actually prove this.
And there's
using
a
Zorn's
quote
lemma.
on the Wikipedia page for Zorn's lemma by, like, Sir Timothy Gowers, who said something like, if you're trying to just build infinite, like, if you're trying to build something that has sort of a pair, I don't know exactly, or what exactly did he say? It's something like something about, like, build, if you want to do something a lot of infinitely many times and you can just sort of keep going, then Zorn's lemma, it tells you that you can stop eventually. Something vaguely like this. You can,
You can get a
Wikipedia
lot
is
of
good.
pretty important results in
But
like
yeah,
algebra from it.
it can help you with, like, handling various stuff about infinity and more advanced math. This is not the sort of thing that is likely to ever show up on any high school math contest, but it's still, like, good to know about, that there's all sorts of neat stuff about infinity out there, and that there are all sorts of complicated issues about logic and stuff, and all sorts of neat math. And in fact, the axiom of choice can be kind of weird in that it can give you some weird paradoxes, which is why there's, in history, it has been maybe a bit controversial, because there's this thing, the Banach-Tarski paradox, which tells you that you can dissect a sphere into two sets and then, like, apply some, like geometric transformation that's like, usually, like just rotating and whatever, or maybe reflecting, I don't know, but like just moving it around in space, moving each set around in space to make two spheres, which, that's really
Of the
weird.
same size?
Yes, of the same size,
But
which is
but
like,
that doesn't really make any sense,
yeah,
right?
it's
Because
like as if I
shouldn't the
said I'm going to
volume of the
take,
first one be the
it's
same
like
as
as if I said I'm going to take this skunk and I'm going to rearrange the skunk and it magically turned into two skunks. Like, that's just so
Whoa.
weird.
Are you cutting off the skunk? That's animal abuse.
No comment. be nice to animals, people. But
Yes.
yeah, so it's sort of paradoxical, but so that's why, and that's why they call it a paradox. But like, basically the point is that the set, volume does not really apply here.
Mhm.
So it's not actually a paradox. We haven't actually broken math. It just seems really counterintuitive. So yeah, the axiom of choice is weird. Infinity is
Infinity is
weird.
strange.
Infinity is really weird, but study it anyway. Yeah.
Yeah, wow. We looked at a lot of different topics today. I hope you all, as our loyal viewers, were interested in the work of underrepresented mathematicians. And if you're still curious, remember that the question submission form is on the Curious Q website. So keep them coming.
Yeah, please, if you please, do research about underrepresented mathematicians. It's good to do that. And if you want, and if you find someone who you think we should talk about,
Send them in.
submit questions. We like to learn about underrepresented mathematicians, or
Indeed.
mathematicians from underrepresented groups.
Yeah, even though I said at the beginning that February was the least statistically significant month, there still have been a lot of things going on, like the Amy. Congratulations to those of you who took the Amy.
Yeah.
Yeah,
Woo.
congratulations to all the Amy takers. So yeah, thanks for listening and see you all next time. Bye.